This is video 30 on MicroPython and the 9th video on LVGL 9 on a Raspberry Pi Pico. In this video, we introduce ulab, a fast math module, and use it with LVGL Chart Wizard. I will describe ulab. Then I will show quick examples of ulab methods and functions using a Jupyter Notebook page. Finally, I will show a quick demonstration of the Chart Wizard and we will review the code. For this effort, I continue to use Pico USB board, the 2.4-inch Ili9341 integrated display. The GitHub site contains the firmware for the Pico, Pico2, and Pico2, and the MicroPython code for this video. By the way, the site contains updated firmware files for LVGL 9.3 for the Pico and Pico2. Your virtual directory files should remain despite the update, but I always back up any files. As this channel covers multiple small system solutions over time, please subscribe to stay informed and click like, as that really helps. ulab was introduced by Hackaday on 29 October 2019 as NumPy comes to MicroPython. However, ulab has only a small subset of NumPy and SciPy. The author built it so that it could fit on a microcontroller. He wanted the most important features and carefully followed the NumPy syntax. The European Space Agency describes ulabs as follows. Ulab is a NumPy-like manipulation library. The module is written in C and is fast. It can be compiled for any platform, and integer, float, and complex numbers are supported. NumPy makes it easy to work with arrays of data. First thing you do is create a NumPy array, and it has many ways to do this. Fortunately for us, you can also create one with any MicroPython iterable. Then all of the features can then manipulate the NumPy array. I used Anaconda to create a Python environment on my desktop, which serves JupyterLab. I pip installed a MicroPython interface. After opening the notebook, I am ready to connect to my Pico. We can connect to Pico using the notebook serial connection command. We are now connected to the Pico. Let's look at the versions that we're running. We are running the ulab version 6.7.4. By the way, we noticed that even though the MicroPython says it's 1.20, it's actually 1.24.1. And the LVGL is now version 9.3. Now let's show you some NumPy arrays and features. First, we need to import NumPy from ulab. In the first example, we create a NumPy array and initialize it. We can use a MicroPython editor directly or from code. Let's see what that looks like. Here you can see X1 was created directly or by running a piece of MicroPython code. NumPy has some shortcut ways. Here's a range. It creates a range of values, 0 to 10 in this case, just like it would in MicroPython. How about a linear fraction between the start and end inclusive? I'm going to do it the same way, but generating 100 elements, each equally spaced by a fraction. We can also initialize an array with just zeros, or with the value 1. Here I'm using a NumPy feature to change the shape of the array from a one-dimensional to a two-dimensional array. Or I can define two-dimension array directly. Finally, I can convert a NumPy array back to a byte string, which I can transmit to another microcontroller or desktop. ulab numby has unary and binary operators. The operation occurs to every element in the numby array. Let's look at the notebook. In this first example, I've got an array A of 1, 2, 3 and an array B of 4, 5, 6. Here we're going to add the two arrays by just simply adding A plus B. Now we have a new array, x10, which is 5, 7, and 9. Likewise, we can multiply two arrays. Now we have an array that's 4, 10, and 18. Here's an example of a unary option. If we want the length of that array, we can see len. That will return the length of the function. ulab numby has interesting functions like interpolate or load an array from a file. Let's look at some examples in the notebook. First, I create a numby array with temp values taken over a period of time. Next, I create the array with the period of 6 days. Now I can use the numby interpret function to get the temperature on day 4. Let's run it. You can see that it's gotten the interpolated value of 76.666. There's a function called load text. It will load a text file. Here I'm loading it from the flash, but I could likewise load it from an external file system, as we've shown in past videos. Since I have a lot of data, it puts the data into a matrix where each row is its own array. So I then use a numby function to flatten it to get just one row. Let's run it. So you can see in the answer, it first read the text data from the flash, put it into an array within an array, and that being the first row. Now I just flatten that so that we have a single array. Then I can get the length, which is 10 values. Finally, I have an example of a SciPy function. Let's take a look. First, we need to import SciPy as SPY. I'm going to perform an integration on the function x squared plus 2x plus 1. Here you see it as it's coded normally. Use the MicroPython lambda function. Here we are using the function quad, which is a technique from the Fortran library QuadPack. We will integrate it from x equals 0 to 5. We get the result and a technique tolerance. Let's run it. Here you see that the integration result is 71.666 and has a very small tolerance. I hope these examples give you an idea of what ulab gives you. We will show another ulab function in our chart code in a few minutes. I built the firmware for Pico, Pico2, and Pico2 in February, and again at the beginning of April, and put it on GitHub. A few days ago, I reorganized the folders to reflect this. The chart demo will use the April firmware. I built the firmware with the default ulab settings. Here are some of the important nuances. The library is 32-bit floating point. It supports complex arrays, is tensors of rank 2, and finally the FFT is numby compatible. I got this by running the ulab_info Pi program provided by the ulab online documentation, also included at my GitHub site. First, we'll go back and disconnect from the Raspberry Pi in the Jupyter notebook. I will click the green run icon. Okay, let's press the button. One array is the Series 1 data in red, and the other array is Series 2 data in green. The min and max value were obtained from the two arrays using ulab, and the y-axis of the chart will be reset to that range. If I press the button again, a new set of data will be generated, and ulab will calculate the new min and max range and change the display on the y-axis. Let's press the update button again. Okay, this is just a sample of the chart widget. There are other features. Before we review the code, let's see the LVGL chart components. An LVGL chart has 3 widgets: the chart's grid object and 2 axis objects based on scale, which we discussed in video 25. A chart can be one of line, bar, or scatter. Notice also there is a runtime step to add a data series to the chart. Now let's open test chart ulab.py in Thony and let's review the code. The first thing we notice is that this program has similar imports as we've used in the past that will work either on our MicroPython or in the simulator. However, I've added a new import for the ulab. Next, I've imported the random function so that we can randomize our data. Next, we have a similar feature to do the screen object as we had in the past that includes the reset button. And here we're setting the screen black. For the UI, I defined a data count with 10 data points. Now let's look at the chart UI object. First thing I do is I pick a width and height for the chart on my display, which I've set it to 240 pixels by 140. Now we create the style and chart. The add flag is needed to allow the axis text and chart to coexist. We set the type to scatter and we leave room for the axis text right here. Now we set the XY axis range, but notice that I provide the new, which is what we're using, versus the old way, versus the old syntax used by the simulator and our previous firmware. Now we start on the definitions for the axis. Remember, the axes are using the scale widget. Here we define the scale and set its size, proportionate to the size of the chart for the x-axis, and for the y-axis we set it proportional to the height. Next, for our scale, we don't want to see the actual bar of the scale, so we set its line width to 0. We position the scale, our axis, to the bottom of the chart. And we do that by setting its Y location, in this case, at about 130. Remember, the size of our chart is 240 by 140. So that's setting it towards the bottom of the chart. Next, we set the range using the data count. And like any scale widget, we set its ticks. Here, I've arbitrarily set the tick count to 10 and a major tick every 3 ticks. Finally, I've set the color of the x-axis to be yellow, and which you can see in the screen. And so that's the digits. So they're all yellow. And the font I made 24, so it's big enough so that we can see in this video. I did something similar for the y-axis, except for I set its starting position for these characters to be 150 to the left within the chart. Here I've set its text values to yellow as well, and also set its font size to 24. Now we come to the data series definition. By the way, I will show you two series, but I found that there's no hard limit mentioned in the doc, and it's very easy to add another day series. So we defined a series with a color and choice of either the primary or secondary axis. So since I'm only using a simple single axis, we're going to use primary. Later, we will load the series with data. Finally, I'm going to disable the scroll bar because if you touch the screen, you don't want to have your chart moving all around. And lastly, I've set the update mode to shift. Now there's two modes. There's shift and circular. In the documentation, it says that shift will shift old data to the left and add the new data to the right, whereas circular will add the data in a circular fashion like an ECG diagram. Though, from my example, I actually saw no difference between the two, and I just set it to shift. Okay, I'm going to scroll past the update code for a second, and we'll go down to look at the button that's on the screen. So at line 161, I began the definition of the button, and you'll see that it's a standard button and label, and I provided a simple clicked button event to call the update data routine above. So nothing fancy going on here. Let's go back up to line 100. By the way, you may have noticed that there's two copies of this routine, and the second one is copied out. That second copy is in case you wanted to use the online simulator, or you're still using the old February version of my firmware. You can comment out this section that we're looking at now if that's the case. But since we're using all the latest of everything, we'll walk through this code. All right, I've created an X array and a Y array. And then I used the random function to populate those arrays with random data, 10 values. Here you can see I've set a default for the minimum and max of the y-axis range. And that's in case you want to comment out the ulab to use in the simulator. All right, let's look at the ulab features. So now I'm taking the array from above and putting it into a numby array for the first series of data and a numby array for the second series of data. I'm going to print it out as you've seen in the shell below here. And then I'm going to use the numby minimum function to get the minimum array between these two and the maximum array. And you can see I've printed out the minimum array as an example. Finally, I use the numby min function, which will return a single value. So what it's going to do is look through the array and look for the minimum value, which in this case is 40, and it will return that to y-min. Likewise, the max function will look through this max numby array for the maximum value and put that into the y-max. And then I printed it out so that you would know what they are. So you can see here in the first example, it was 40 and 73. And so now I use those values to set the chart's axis range on the primary axis to those min and max values. Likewise, I must also set the y-axis scale from y minimum to y max. So you have to do both of these, otherwise your chart and scale will be out of sync. Now there's several ways to load the data. Since I created all these arrays for the ulab example, I'm using the function called setSeries external X array and setSeries external Y array. So now I can just populate the series with these external arrays, and then when I perform this chart refresh function, that will actually refresh the screen and display the data. Let's try it again. All right, you can see how fast the ulab performs those very sophisticated manipulation of those arrays and functions and gives us a new chart. In summary, we researched ulab. We demonstrated its capabilities using a Jupyter notebook. We discussed the specific firmware available at our GitHub site. We reviewed the program code of a chart wizard and used a couple of lab functions within it. Now you should see how easy it is to include ulab in your LVGL projects, and it provides a lot of power while simplifying the code. I hope this video helps your LVGL MicroPython coding. Thank you for listening.